I'd like to introduce Alex Elmore, who's going to talk about significant damaging wind events in the St. Louis National Weather Service County Warning Area.
All right, thank you. Yes, as he said, my name is Alex Elmore. I'm a meteorologist here at the St. Louis WFO. I'm going to be talking about significant damaging wind events in our county warning area. And when I say significant damaging wind events, those of 80 miles an hour or greater. So this started, or I guess you could say this project started given what happened back in the summer of 2021, which is that, as we know, we implemented a tiered approach to issuing severe thunderstorm warnings based on the size of the hail or wind gust, magnitude of the wind gust expected within a storm. And with the destructive warning, specifically for wind being 80 miles an hour or greater. And there's a lot, obviously, that rides on those warnings and really those events, and it's because of the impact of those events, right? There's a reason that those warnings trigger WEA, and here locally, we've gotten all of our Metro St. Louis counties on board with also sounding the sirens when we issue those warnings with the destructive tag. And I believe our next step is to get all the counties within our CWA on board with issuing or sounding sirens for these types of severe warnings when we have 80-mile-an-hour wind tag there in the warning. So there's a lot that rides on this because the impact to human life and property is obviously greater. And this approach, this tiered approach, is very similar to, or kind of similar at least, to how we've been issuing tornado warnings for about the last decade or so, right? We have various tags we can apply to tornado warnings, and that's based on thorough analysis of radar imagery, mesoanalysis, just understanding what the environment and the storms within it are capable of, and applying or correlating that to what we're seeing on radar and applying tags appropriately so that the public and our partners are getting the best information possible. And a lot of how we do that is backed by years and years of research and studies. When it comes to at least damaging wind gusts, there is literature out there. There has research been done that looks at severe environments versus non-severe environments, and general overall storm features that are associated with damaging wind gusts. Kind of a yes or no approach to, is the storm capable of producing damaging winds? And there are studies that focus on the environments that are capable of producing long-lived wind events, derechos, and significant wind events. But comparatively and relatively speaking, there's not as much literature available and guidance available for determining the magnitude of damaging wind gust within a storm, compared to how we're able to diagnose the tornadic potential and magnitude of a tornadic storm. And this does, this is for good reason. It's very difficult to diagnose the magnitude of damaging wind gust. Phil Schumacher, Sue at Sioux Falls, has done some work recently looking at verifying tags within severe warnings. And what he's found is that it shows that we do well at determining yes or no a storm is or is not severe, but we do have a little bit more difficulty in determining the magnitude of severe, when it comes to both hail and wind. And so the point of this climatology, if you will, is just a teensy tiny baby step toward hopefully bettering our ability to be able to diagnose these higher end wind events before they actually occur, before we're getting reports of destruction and significant damage. So had this slide just in here just to make sure folks are aware that I'm aware of the many caveats of wind reports and the various data sets that we have. It's covered extensively in the literature, but I picked just 3 papers that I felt hit the highlights of some of the issues we face when we're going back and looking at archive data. Daswell et al. In 2005 talked about kind of the issue of if a tree falls in the forest and no one's around to hear it, doesn't make a sound. If a wind, you get a damaging wind event, or a wind event that is above severe criteria, and it's not sampled properly, like, then that's an issue, right? Did it happen? How did it happen? What was the actual magnitude? Wind reports aren't, or wind events rather, are not just they don't just occur at a specific place in a specific time. They're likely occurring over a period of time and over a swath of area. So just kind of talking about the issues with properly sampling events. Edwards et al. In 2018, that's a relatively recent paper that was talked about quite extensively there for a while, but just the focused on the human bias in estimating wind gusts. And typically, we as humans, we overestimate the actual wind magnitude. And then Trapp et al. In 2006 talked about storm data and how it seems that we under-characterize significant wind events and over-characterize relatively weaker wind events. So just all these issues taking into account, looking at this sort of data set. For at least right now, I did not, when it came to the wind reports, I didn't filter out estimated versus measured. That will be done in the future, but for now, all the data, it's just all the reports estimated or measured of 80 miles an hour or greater that we received. So this is the St. Louis CWA there, LSX. They're in the middle, kind of a Texas shape looking CWA, if you will. And I looked at reports from 2000 through 2022. And overall, this is a time series just showing all wind reports, so 58, or severe wind reports rather, 58 miles an hour or greater. They're that yellow line, and then I broke it down by now that tiered warning system, if you will. So 58 to 69 miles an hour, which is your base warning, is there in the orange. The red line is 70 to 79 miles an hour, which is considerable, and then 80 miles an hour or greater, destructive there in the purple. And we see generally, as far as that considerable to destructive category goes, generally, that's kind of, there hasn't been much trend over the last 20-ish years or so, but we did notice an interesting downward trend in kind of the overall severe wind reports, as well as the base severe warning reports, if you will, 58 to 69 miles an hour. Not really sure why exactly that's happened. Some of the veterans who have been here for a while, just noticed a general decrease in the amount of severe storms we've seen here locally, but can't confirm if that's exactly the reason why, and it was beyond the scope of this particular study. So looking more closely at those 80 mile an hour or greater wind reports by year, the blue line is just the number of reports, and then in an attempt to kind of normalize the data, I broke them down, or kind of condensed them down into events. So like if there was a QLCS that produced 5 80 mile an hour wind or greater reports over the swath of a county, that counted as a single event. So just kind of a way to normalize the data. And some of these spikes are driven by particular events. Back in 2013, there was the BAMX field experiment that was going on locally, and there was a strong QLCS that went through the St. Louis metro area and portions of the Metro East that was very thoroughly analyzed by the field team. So that's why we see that bump there in the early 2000s. Then in 2006 is the infamous July 19th derecho that hit the St. Louis metro area head on. There's a couple videos if you search on YouTube from Busch Stadium, where the St. Louis Cardinals play, of first year the stadium was open. Not sure what type of shelter protocols they had, but there's a video of folks staying out of the way of an entrance, which is turned into a wind tunnel, and there's a trash can that goes flying through that entrance and hits somebody. So that was a pretty notable event. Lots of tree damage in the area, but yeah, that's why we see that bump there. And then here in the early 20-teens, that was just a particular busy couple of years. But generally, we do see a couple of one or two of these events, or maybe a little bit more every year here in the St. Louis CWA. So when we break them down by month, I was expecting to see a little bit of a shift more toward the summer months, just given I'm thinking, okay, your more significant wind events, they're driven by MCSs that are formed from convection over the plains, kind of riding down a thermal boundary or instability gradient into our area. That happens quite often. But really, the frequency in which we see them, it's focused more so in the spring, when we see our overall climatological peak of severe weather. So that goes for both the reports and the events of 80 miles an hour or greater. We do still see plenty in the summer, but that's that focus more so in the spring that we see these events. So I looked at each report using GR Analyst archive radar data, and I was fortunate that I believe a majority, if not every single one of the reports we had over that time period, did have radar data available, that I was able to put the report into one of 4 storm mode categories. So there on the left, we have kind of your typical like summertime MCC, MCS, MCB, developing a convective complex that moves through the area at some point during the day, primarily damaging wind event. And then up kind of in the top left, we have QLCS, so kind of a smaller scale linear system, Boeing segment, if you will. And then supercell, discrete supercell, up there in the top right. These, even though I just have the label here as supercell, typically these were HP supercells. There were only a couple of events where we had it was more of a classic supercell structure. A majority of these were HP supercells. And then, of course, single multi-cell thunderstorms. Think kind of like your downburst events that are producing those 80 mile an hour or greater wind reports. And when I look at just the reports, so not taking into effect any sort of normalization, we see that over the period of from 2000 to 2022, we see that QLCS storm modes gave us a majority of our 80 mile an hour or greater wind reports, with supercells following closely behind. But when we look at the normalized data, so just looking at events, not counting each individual report, we actually see that discrete supercells are the mode that drives the majority of our 80 mile an hour wind events. And that kind of makes sense now when you think about the seasonal climatology, that we do see it more so in the spring. When we're, at least here locally, we have greater shear that we can get these types of storm modes, versus more so over the summer when we don't have a lot of shear to work with. So with each of those 2 primary storm modes, I broke them down into individual storm features that were directly associated with the wind report. So up here, when we're, looking at QLCS storm mode, up here in the top left, we have bow echo or rear inflow jet. That is the primary driver for the report. So these reports occurred near the apex of the bow. There wasn't any from what I could tell, a mesovortex associated with the damage. It was just the rear inflow jet there surging out into the line. Bottom left, your bookend vortex on the northern end of a linear system. Up here in the top right, mesovortex. So this is a report that was directly associated with the mesovortex, the couplet itself. And then we had cases of mesovortex and rear inflow jet combo. So these are reports that occurred kind of on the southern periphery of the mesovortex and the northern periphery of the rear inflow jet. And the importance of that particular area of a QLCS has been the focus of past literature. So Atkins et al. In 2005, this was looking at June 10th, 2003 QLCS that impacted the St. Louis metro area that I brought up prior. And they noticed a localized area of enhanced winds where we did have 80 mile an hour winds or greater, a pretty large swath, was associated with a mesovortex that occurred on the northern periphery of the rear inflow jet. So you have that cyclonic flow around the mesovortex pairing with the surging rear inflow jet to cause that localized enhancement. So that's what, when I say mesovortex plus rear inflow jet, that's what I'm talking about, is this kind of they're teaming up this combo of features that's producing this localized swath of 80-mile-an-hour winds or greater. And we see that, when we break it down by storm feature, it is that mesovortex and rear inflow jet combo that drives a majority of the 80-mile-an-hour wind reports that occur within QLCS storm mode, followed closely by just the apex of the bow or rear inflow jet. Now, when it comes to HP supercell storm mode features, I broke it down into three primary storm feature categories: the RFD of the storm, or as it's growing up scale and the RFD is surging and kind of taking over. So I'll get into describing that a little bit more detail here in a second. The other storm feature was a mesocyclone, so I couldn't really distinguish whether or not it was more so in the rear flank downdraft or in the forward flank downdraft. It was just directly beneath the mesocyclone. And then lastly, we did have a handful of reports that occurred within the forward flank of HP supercells. And so when I'm talking about that RFD and surge phase of an HP supercell, talking about this kind of this evolution that was described in Muller et al. In 1994 and several other researchers throughout the last couple of decades, where through the HP supercell's life cycle, there is the potential for the RFD to take over and begin driving the storm and causing it to bow out, as we see kind of steps 3 through 8A up here in this schematic. And from what I could tell, generally it was, as we get from steps 3 through 7A, is when we noticed that that was when those 80-mile-an-hour wind reports occurred. Like once the storm had grown completely upscale, I guess you could say step 8A here, we didn't see, it still produced damaging wind, but it wasn't to the same magnitude as it had prior when it was evolving. And that particular evolution and just the RFD of HP supercells is where a majority of the reports associated with supercells come from. And that particular evolution has really fascinated me over my time here as a NWS meteorologist. One of my first warning events was back in July of 2021 in northeastern Missouri, where we had a squall line catch up with an HP supercell and merged with it. And we see this HP supercell wind up, and just its mesocyclone, you can still call it that, really broadens, and we see this enhancement of the inbound velocities within kind of the, I guess you could say, the surging portion, the RFD portion. And this I know the county boundaries aren't too easy to see here, but through the entire north-south length of this county, it carved at least a 70-mile-an-hour swath through the county with a pretty large area of 80-mile-an-hour winds, and then several areas of 90-mile-an-hour winds, where we had folks that reported a very like 20 to maybe even 30 minutes of 60-mile-an-hour plus winds. So a lot of folks in that area described it as almost like living through a hurricane, just with the prolonged wind and rain. And we see of the 29 reports that are associated with this evolution and this Boeing feature, 18 of them resulted from mergers that fit that upscale growth model that I described in the slide prior. There's been a lot of research that has focused on I guess you could say, this evolution as a result of mergers. King and Presbolinski, in a paper they wrote back in 2004, talked about a very similar looking case of an HP supercells interacting, and then one grew upscale to produce a swath of 80+ mile-an-hour winds just south of the St. Louis metro area. French and Parker in 2012 did a paper that was a climatology of such events. And then they've also been simulated, for example, Finley et al. In 2001, and then French and Parker in 2014 did several simulations. And from that French and Parker paper, in 2014. I pulled a quote that they said, "These features common to severe bow echoes are shown to be a direct result of the merger in the present simulations and are diminished or absent in the no merger simulation." So basically, this evolution that we see here playing out in this GIF, like this Boeing, it doesn't happen, or their simulations, they didn't get that unless they had a merger. And so this can be a key. Like, again, this is nothing new. This has been covered, extensively in the literature over the last couple of decades, but it's important for us as warning meteorologists, if we want to get accurate warnings out, that we, maybe we pay attention to these features a little bit more. I'm not saying that every merger is going to result in, HP merger is going to result in this sort of evolution, but, it's something that, we need to look into more to see, like, hey, if this happens, how often do we get this upscale growth that causes a surge that produces this magnitude of wind, so that we can produce accurate warnings, get people to take shelter appropriately when they need to. So that pretty much wraps it up. Just kind of an overview. Generally, for us here in the St. Louis CWA, we see 80 mile an hour wind reports. Their temporal climatology fits that of our overall severe climatology, so they peak in the kind of mid-spring, and that makes sense given the storm mode that we saw. That's the primary driver for them. QLCS storm modes produced the most reports, but HP supercells, when you normalize the data, resulted in the most events. And the primary storm features within those QLCSs were the mesovortex paired with the rear inflow jet. Again, you get that combo, just that flow around the mesovortex pairing with the rear inflow jet to cause that localized enhancement. And then when it comes to HP supercells, we see that the primary storm feature or phase of the HP supercell is when the RFD, or when that RFD is surging out. So if you have any events that are like this that you want to share, or you have any questions, or maybe insights from your own area, by all means feel free to reach out and let me know, or ask any questions. And if there is time, I can take any questions now. Thank you.
Great job, Alex. That was a great talk.